And first of all, let me just say that I'd like to thank Eli and all the organizers for giving me the opportunity here to talk about some of the efforts we are currently working on in UC San Diego, Nanowire NEMFET. And I basically help you spell it out in the title right there. It means Nanoelectromechanical Field Effect Transistor. So emphasize on the FET. So I always tell people first of all that the nonce name is a FET, and we just put in the NEMs before it. So I'd like to also thank the two PhD students that did all the work, and also the funding agencies. So before I talk about NEMs, I'd like to go back a little bit, actually, to talk about this topic we've been hearing about for the last couple of days, MOSFET. So I think at this point, we've been reminded multiple times that it is very important and maybe even imperative to have very steep subthreshold slope so that we can have a very small off current and very small static power dissipation for energy efficient electronic systems. Well, unfortunately, as we all know now at this point, the subthreshold slope is linked to the kBT over Q factor, which is a non-scaling factor because, as we all know, we all live and work in this ambient environment. That means we just cannot scale temperature towards zero. So that means we're going to see this finite tail of the Fermi-Dirac distribution, which gives rise to this tiny little but yet finite diffusion current. So when you try to turn a device off, you try to do it very slowly. So the result is we have to spend a fair amount of VDD to turn the device from on state towards off state, and a portion of it, about 20 to 30% of VDD, is spent on this subthreshold region. Well, what a waste, right? So I think you'll agree with me that we all want an ideal switch that can get rid of this subthreshold region, and just when we flip a switch, it turns up very, very sharply. So with infinite slope or a subthreshold slope of zero, right? So if we have this switch, then we can get rid of the wasted voltage applied on the subthreshold region. We can use much smaller VDD to turn the device on and off. So, there are ways to do this, as we have heard from this morning and all the way from yesterday. For example, using the quantum tunneling principle or using the ferroelectric transition in the negative capacitance model to try to switch the device on and off using a principle that is not dependent on kBT. And it works to some degree that people have made and also predicted the devices that switch much steeper, but not as steep of zero, right? So today, I'm going to show you another principle, which is the mechanical degree of motion, as you've heard about from the previous speaker, Philip. So here, what we're doing is basically take a FET with the same source drain and the current through this channel, and have this device move towards the gate, so that this mechanical degree of freedom will make the device switch from an on state to the off state where it is closer to the gate. And this motion, this mechanical motion, is abrupt and it does not depend on kBT as well. So that's what we're hoping to achieve. So, this idea is not new, as you have seen examples from Philip's talk. As a matter of fact, a few years ago, this idea originated from right here, Professor Jie Xiang's group. And actually, I think this paper in 2005, IEDM, is probably one of the first ones that mentioned the title NEMFET. So they proposed this device that uses a movable gate, poly gate, where they predicted that at a certain gate voltage, the device is going to pull in, the gate is going to pull in towards the channel, because of the electrostatic attraction effect. And when you release the voltage, sweep back the voltage, it's going to slap back or pull out to the original state. So multiple people have since worked on this idea. For example, Philip Wang's group, as well as Adrian Ionesco's group in EPFL. So, and people have made, for example, EPFL has made this device, rather bulky device that proves this idea. It works. So here is a suspended gate MOSFET that is rather big. I mean, I want to point out 10 micron scale bar. So, but the problem is, since it's very bulky, very big, it works very slowly. The resonant frequency is about 16 megahertz. And more importantly, the voltage is very high to switch it. And the difference between the pull-in and pull-out voltage is 5 volts. It's really high. It's really high. So we started working on this idea and try to bring nano into it. So we try to scale this device down into the NEMS scale. So what is NEMS? We heard a lot about it. Basically, they're tiny guitar strings. And literally, guitar strings made from silicon carbide nanowires has been demonstrated in Caltech in the Lucas group that has a fundamental resonance frequency of gigahertz. So that's what we're going to start with. NEMS promises very high speed. But before I tell you about the NEMFET, so just want to quickly comment that NEMFET is not the metallic contact switch that you heard about earlier. So we do not rely on the metal-metal contact or metal semiconductor or carbide contact. As we heard before, we'll have this hot switch, cold switch problem because when you have two metal switches contact to each other, if you're not careful, you apply large voltage, you know what happens when you pass large current through this two metal contacts. So that's not what we're doing here. Instead, NEMFET, our NEMFET, has source and drain, has fixed anchor acting as source and drain through a semiconductor channel, in this case, a germanium nanowire, passivated by a epitaxial silicon shell. So this has diameter of about 15 nanometer. The shell's thickness is about 2 to 4 nanometers. So the nanowire is naturally a PMOS, a PFET, working in accumulation mode. We already know that. So it's normally on, but when we apply a gate voltage, it attracts this channel towards the gate. Eventually, up to a certain threshold, it's suddenly pulling towards the bottom and becomes depleted. So essentially, so we did a simulation. So we are switching between the top curve and the bottom curve, which is the on state and the stock state, where the transition from the on current and off current occurs abruptly. So this way we can achieve very sharp turn on and pull out, all within a very tiny voltage window. This is based on 10 nanometer air gap simulation, by the way. I want to point out also, our study also suggested that the device, you have to be very, very careful with the design. The channel doping, for example, if you vary by 3 times, as you can see here between the blue and the red curve, you can get from anywhere from very, very lousy on-off ratio to very excellent on-off ratio, all because of the threshold of the stuck state, threshold voltage of the stuck state. You want it to be as far away as possible from the top state. So I'll tell you about the implication of that when I show the experimental data. So I skip to our latest results. So this is the latest device we've made. So we use differential thickness of the anchor and the gated electrode to define the air gap, and we put a nanowire on top. And eventually, I want to point out, so we use this ALD, hafnium oxide deposition, to define, to first of all passivate the nanowire, but also to shrink the air gap even further. So this way, we have atomic control of air gap reduction. We can reduce it atomically, layer by layer, as much as we want. So the end result is this. So the nanowire has a diameter of 25 nanometers plus 10 nanometer hafnium oxide on either side. You can see a little brighter ring on both sides. Air gap is 35 nanometers. It was shrunken from 55. We deposited 10 nanometer hafnium oxide up on top, and the bottom shrunk it to 35. And the size is 1.3 micron length. So here's the result. So this is data from a NEMFET, and we successfully demonstrate sharp pulling to off current is 12 millivolts per decade. But that's not real, because this is really limited by that's really the size between this on current point and the off current data point. We just couldn't make it any sharper. So, in some other cases, we can see from this other sample, we have 6 millivolts per decade a device with about microamp on current and a few hundred picoamp off current on-off ratio of a couple thousand. So one thing you notice, the voltage is really high still, right? But I'd like to point out that what really matters, I think, is this window between the pull-in and pull-out current, which is really reasonable in this case, 1.6 volt, because really in CMOS, it's not a trick. It's pretty regular for people to drag around the absolute value of the voltage by playing with gate walk function or planting fixed charges. So the device works multiple times And we found out the pulling voltage increases slightly at the very beginning, but becomes stable. I just want to point out that the window between pull in and pull out is also not only very stable, but it's very small, reasonable as well, 0.83 volt in this case. So the last data I want to show you is, unlike the metallic switch or carbide switch case, it's very hard to characterize the speed. In our case, we can actually use the MOSFET, the NEMFET, as a heterodyne mixer because it has nonlinear transconductance. So we can very easily mix it down to 400 hertz and characterize the AC property, which shows this is 126 megahertz, already VHF frequency, FET, and we can see a hardening effect, almost a linear hardening effect with VG, so suggesting there's no slack. So this nanowire putting anchor between the two contacts has no slacks, very, very good quality. And the bias dependence shows a little bit of capacitive softening. That's a topic for another day, maybe. So before I finish, just want to point out a little bit a future direction. So in this field, it's really important to be careful when you design material. But obviously, you want to shrink the size, the length, and the diameter as you scale down. For the scale down, is what we're trying to do to get higher speed, as the solid line signifies. You go to 200 megahertz, 300 megahertz. But also the pulling voltage, you got to watch out for the pulling voltage. You get a more rigid device, it's going to make it harder to pull in. So the color map is a constant pulling voltage map. So and the dotted line is the constant pulling voltage line also. So the intersection tells you what device you want to design for. In this case, we fixed the air gap with 10 nanometer. It shows that you can basically make a sub 1 volt absolute pulling voltage with a 5 nanometer nanowire. And we heard from a lot of speakers today that you can use 2D materials or even carbon nanotubes, graphene. So all that is what is the direction that we're going to pursue in order to push this NEMFET concept even further, so that we can have our ideal switch with zero substrate slope, but then acts every bit as a PMOS at the on state. Thank you.
About the dynamic of the nanowire, do you see any limitation coming from the amplitude of the oscillation induced by thermal?
Well, that is a good question. So first of all, let me clarify. The AC measurements here is very small in terms of driving amplitude. This mechanical amplitude is probably a few hundred picometers. And on the other hand, the actual NEMFET operation, it is quite nonlinear, far from linear, because we put it down all the way to 35 nanometers at the center of the nanowire. So the nanowire itself behaves much more in the nonlinear regime. So that raises a lot of interesting questions. And I, Philip, and most people in the community will be glad to figure out more ways to probe the dynamics property of during the actual NEMFET operation.